So this is Alessandra's last lecture. So it's our last chance to learn about modifier beyond LCDM in general. So should we continue discussing the effective field theory of dark energy?
Okay, yeah. Thank you. Thank you for making it. And I'm going to finish sharp at 10:30 because I have a flight to catch. So I want to talk more about, I didn't turn it on here, more about EFT of dark energy, and I'm going to just jump to it because I've said already a few things about it yesterday at the colloquium. So let's look at it as a way of orderly building up extension away from the Einstein-Hilbert action. So I start with the Einstein-Hilbert action. And while I haven't written it here, perhaps it will appear at the end. There's also matter with its own action. And by the fact that I'm saying we are in Jordan frame, it means that I'm considering that the matter couples to the metric and follows geodesics determined by that metric. That's an assumption which can be quite strong in the sense that I'm assuming that either there's no coupling between my dark energy and matter particles, or it's a universal one. And if it's not a universal one, the other way I can get out of there and find a Jordan frame is by saying I focus only on dark matter. So I use the coupling to dark matter to be the one that helps me determine how to go from Jordan to Einstein and vice versa. So it's not too stringent of an assumption, at least it's very common, but it is there. And then we start going beyond that, and we can, of course, have the cosmological constant or make it dynamical. And here you recognize the conformal coupling. That's the object that we encounter in Brans-Dicke, for instance, in generalized Brans-Dicke. It's a typical thing that appears in a Fauvar. And if you look at the Fauvar as a Brans-Dicke type theory, and it means that your scalar field is not minimally coupled to gravity. And if you go to Einstein frame, it means that it is coupled to your matter particles. What am I doing here? I'll explain it a bit more in the next slide, is giving a kinetic term to this scalar degree of freedom, okay? I'm just writing it in a bit of a cumbersome way that will be clearer with the next slide, where I show a sort of mapping for this language. But the idea is that I'm not really introducing explicitly here a scalar field. I have absorbed it in the metric, something similar to what you do, you might have seen in quantum field theory. So here I'm absorbing this extra degree of freedom that we are used to see as phi, a scalar field, into my metric degrees of freedom. And so it's showing up here in the perturbations to delta G 0, 0. So if I stick to this line, I'm just introducing a dynamical scalar field with a standard kinetic term and a possible non-minimal coupling to gravity. So generalized Brans-Dicke, Fauvar, and all those theories are in here.
So just to clarify, the scalar field is in the metric?
Yes. I show it in the next slides, exactly. In the next two slides, I'll try to give a flavor of how you do that mapping. But it's in there. And you see it because now I have this loose indices here. And that means that and I have also explicit functions of time, right, in my action. So I've given up invariance under time diffeomorphism. So the idea is that I have a scalar field, so it sort of gives me a preferred foliation of space-time. And I'll show it in the next slide, which foliation is this. So I can adjust my coordinates in such a way that I absorb that scalar field in my metric. But by doing that, I use time diffeomorphism, and then I lose the invariance under that, right?
And capital omega?
Capital omega is a function of time.
But it has a field interpretation to it? Or?
No, there's no field interpretation to it. I mean, it is related to your scalar field, but no. No, this is just a function of time that will tell you about the coupling of your scalar field to R. And then, so the other thing I should say is that we want to have an action that is up to quadratic order in the perturbations, because we want to study background and linear perturbations, okay? So this is an expansion that I could keep going forever, but I'm stopping at quadratic order in the perturbations. Of course, here I'm looking, for instance, at perturbation of the Ricci scalars, perturbation in the metric, and then I have to open these and expand each of these in the perturbations of my, like that are in the perturbations of the metric. So this, in principle, could be a higher order term in perturbations, but when I will do the expansion, I will stop at second order. And so whenever I leave this line and I start opening operators such this, not only, so what I'm doing is that I'm having a scalar field with, which has a typical behavior of Galileans, so has non-trivial kinetic terms, higher order derivative couplings, and things like that. So let me maybe, this is overwhelming. Let me go, yeah. Yeah, so let me go to the next slide where I show you all these objects, what they are. Okay, actually, the one after this. So this is to describe how I fix the unitary gauge. And so you can think of having your scalar field as a function of time, and then on top, perturbations to that scalar field. So the overall scalar field can be a function of time and scale, but we reabsorb those perturbations into your time coordinate. And you resit basically your scalar field on the background solution. And the way you can do that is because the scalar field sort of single out a preferred foliation of spacetime. So you can separate your spacetime in a set of hypersurfaces of constant time that you make coincide with hypersurfaces of uniform scalar field. It's like the scalar field becomes your new clock. It gives you a natural direction flow for your time, and you adjust your spatial hypersurfaces, those of constant time, to correspond also to those of constant but also uniform scalar field. So this is the unit vector. This is just to make it a unit vector, the normalization down here, that indicates that is orthogonal to your spatial hypersurfaces. So let me be a bit more specific about all those geometric elements that you saw in the action. And so the good way of looking at that, a very natural way of looking at this, is the so-called AGM decomposition, Arnold-Deser-Misner decomposition of space, where you actually choose these hypersurfaces of constant time, where you will have your spatial metric describing you these hypersurfaces, and then you have also to tell me how you how you distribute them in the four-dimensional spacetime, right? And so you will introduce a lapse function that is telling you basically how you progress in time with these different hypersurfaces, and the shift vector, which is also connecting, telling you basically about the anisotropy in going from the different hypersurfaces. And now, of course, we start from a four-dimensional metric, but I can always look at the one characterizing my spatial hypersurfaces, h mu nu, which is the projection of my metric on these spatial hypersurfaces. And there are two objects, two types of curvatures that we can then think of. One is the intrinsic curvature, and one is the extrinsic. And the very good way of thinking about that is by taking a piece of paper, which is flat, on which you have Euclidean geometry, and it has zero intrinsic curvature. But if you roll it up in a cylinder, so you embed it in your three-dimensional space by rolling it up, you give to it an extrinsic curvature, just because of how you're embedding it in the higher dimensional space. So there are cases, I mean, intrinsic and extrinsic curvature can be two very different things. And the extrinsic curvature depends on how you embed your hypersurfaces in the four-dimensional spacetime. So now here there's a lot of geometry in defining these objects, so these are those objects that we were seeing in the action. This I have already said it, right? Now, since I have given up, since I have used my invariance, let's say, under time diffeomorphism to choose this foliation, to choose this unitary gauge, now I have whatever, what I can use to build my action are all the geometric invariants, all the geometric things that are invariant under the remaining part of my diffeomorphism invariance, which is the three-dimensional spatial diffeomorphism invariance. That's why, so you can combine all these objects, the intrinsic curvature, the extrinsic curvature, and so on, to build all possible combination, up to quadratic combination of geometric objects that are invariant under three-dimensional spatial diffeomorphism. And on top of that, you can also introduce functions, explicit functions of time in your metric. So,
you don't have, so phi, yeah, where is phi?
Yeah, so let me show, yeah. Okay, so maybe this answers to the question. So how I defined this foliation, of course, was by saying that phi is my new clock, right? So if you want, another way of thinking about this is thinking that since you're sourcing acceleration with something that is not a cosmological constant, you are spontaneously breaking time diffeomorphism invariance. And phi is there, and...
You don't see phi in the Jordan frame. That's why I'm confused.
Yeah, you don't see it because I've written the Jordan frame. Oh, sorry, what do you mean you don't see phi in the Jordan frame? You usually, or you didn't see it in my action that I showed? Yeah, no, because it's in the metric. Yeah, it's hidden in the metric. Yeah, but you could rewrite it. So that's how. So I was ambitious. I thought I would do the whole calculation showing you the mapping for a model today on the board. But then yesterday they didn't let me work. So I'm not going to do the calculation. It's a very long one, and I'm going to get lost if I try to do it. But there's nice papers out there that do the whole calculation. But let me give you a little bit of an idea of how you should proceed. If you have a typical covariant action where you have your scalar field appearing, let's take, I don't know, even quintessence, simple quintessence, or a Galileo model. So you will have this action as a function of phi and x. How do I go from that action to something that was like the one that I showed before? And there's a couple of papers that are really good for that. And I think the first one where I would start from is one by Paolo Creminelli and Guido D'Amico, where they do the EFT of quintessence, which was the first step towards this EFT of dark energy. And then there's a couple of very good papers by Jérôme Glazes and collaborators. He was a student of Filippo Vernizzi, so there's typically also Filippo in those papers. They describe very well how to do this mapping. It's a long calculation, the mapping. But the underlying idea indeed is this one. So you start by defining your hypersurfaces and the unit vector orthogonal to these hypersurfaces, orthogonal to these hypersurfaces. And then, okay, here I'm just calling gamma this normalization factor, this inverse of the square root of my kinetic term. Here's how I've defined the kinetic term. Okay, semicolon in principle indicates covariant derivatives, but of course here it's acting on a scalar field. The extrinsic curvature, this object that is describing the extrinsic curvature of your spatial hypersurfaces, can be built out of this unit vector combined with your spatial metric. Okay, this is one way of writing this extrinsic curvature. There's an acceleration vector that you can associate to this unit vector. In most of the theories, this is 0. In most of the standards, there's some version of what is known as Ojava-Lifshitz, a non-projectable version of Ojava-Lifshitz in which that is non-zero. But so in general, you can keep it. And then you can do this exercise, given these definitions, you can try and convince yourself or open this paper and look at the calculation that typical objects that you might encounter in your actions, such as, for instance, the D'Alembertian and the second derivatives, these are, yeah.
So, mu is a time like that, right?
Yes.
Is it unit
Depending on, yes. So n mu is, well, now I might get the sign wrong. It's like this. But then the upper one, the one with the upper index, will have also a spatial component. Okay, so you have to be careful in when doing that. I don't know now. I mean, but there is a spatial component which is related to the shift with some normalization to the shift vector. So you have to be very careful with the indices. And these are typical objects that enter in the action for Galileans. You are not used to see them in the standard quintessence, for instance, where you have a simple kinetic term. But we have higher derivative terms. They are typically coupled also to geometrical terms, such as the Ricci scalar, etc. And it's possible, from this definition up here, to work out the expression of such terms in terms of these things such as the extrinsic curvatures, etc., and your unit vector. So that's the first step that you should do in going from your covariant action to writing it in this geometrical language of the unitary gauge, where you have absorbed your scalar field in there. It's a lot of math. I mean, the simplest case that you could do is that of quintessence to try to convince yourself. But otherwise, you can also try this and take a simple Galilean, I don't know, the cubic Galilean, for instance, and try to do the mapping. And you will see that it's possible to get to that original action that I showed. And so your scalar field and the perturbations in particular to your scalar fields will now enter in things such as delta n, perturbation to your lapse, delta k, perturbations to the trace of your extrinsic curvature, and so on. That's where you absorb the typical things such as delta phi that you would see if you expand your covariant action into quadratic order in the perturbation to the scalar field. The mapping, you do it at, we are interested in the mapping up to the quadratic order in the action. And OK, so if you do that, and you can try it if you're interested in this, you can try the exercise, you will get the action. And the interesting thing of that is that this is a precise mapping. So remember that framework, mu and sigma, mu and gamma, whatever, which I build at the level of equations, right? I have minus mu at the level of basically relations, and let's use sigma. This is the simple, as somebody reminded me yesterday, I should specify this is, I'm specializing to the simplest definition that doesn't take into account the neutrino shield. But so, you see, the way we defined mu and sigma, the only possibility that we had in order to specialize to a specific model of gravity was going to the quasi-static regime, or was to solve the model, numerically find mu and sigma, and have a numerical expression for mu and sigma. But if I want to find analytical expressions for mu and sigma, like those that I gave you for FOVAR, for instance, right? Mu in FOVAR is 1 plus this, and then there is, I might be getting it wrong here. So this is in the quasi-static limit. So I can have a sort of mapping of my models into the mu and sigma language only if I go to the quasi-static regime. With this approach, it's very cumbersome to work out the mapping. It's something on which you improve the more you do it. But you have it for all of those models, like FOVAR, all those Galilean Hordesky models, and you can go also beyond. You can work out a specific mapping at quadratic level. So you will, what I'm trying to say is that if I tell you do a FOVAR, you can tell me what is omega of tau, c of tau, and lambda of tau as a function of your FOVAR. You can find analytical expression for those. I don't need any of the higher order operators in the action if I'm describing a FOVAR. It's a GBD model. And it turns out also, and you could have expected, we've seen that the scalar field, the scalaron in a FOVAR doesn't have its own kineticity. And so you will expect C to be 0. So FOVAR is a very simple subcase of this CFT language. And now I don't remember by heart, but this will be something related to F sub r, and this is something related to the potential that I don't remember what it was. But so you can work out an exact expression. So there is a mapping. I don't need to resort to quasi-static approximation. So that's the first thing that made us interested in this approach, because we were very unhappy when playing, for instance, with MGCAM, that we had to always rely on this quasi-static approximation. So we thought, now we have a big umbrella, and even relying on the quasi-static approximation, finding expression for mu and sigma for more complicated models can be a pain. So now we had this big umbrella for all these models. Hordesky, when we started, now you can go a little bit beyond that with this formalism. And for each of these models, we could find a specific mapping. And so the idea we had was like, okay, so if now we implement this in CAMB, and similarly, other people implemented an analogous framework in class, we have one code that can be used to study all the models that are inside Hordesky, for instance, and without relying on quasi-static approximation, evolving the full dynamics. Of course, it sounds really nice. It's a lot of work. It took us a year or so to do it because, first of all, out of that action, you have to work out all your Einstein equations. And it's a lot of equations. I mean, it's very long equations, complicated. You make a lot of mistakes, and you have to, for months, compare and fix them. And then you have also to implement them in CAMB in such a way that is efficient, stable, et cetera, et cetera, et cetera. So there's a lot of work. But eventually, if you do that, and especially if you're able, if other people do it and you're able to validate the codes, as we did, then you have very useful tools in your hands. So the one thing I should say is that the unitary action is, although it maybe doesn't look so nice, it's really nice because it gives you this sort of underlying rules to build all the terms that you put in there. You say, I'm spontaneously breaking time diffeomorphism, and now I expand in all the operators that are invariant under 3D spatial diffeomorphism, and I go up to quadratic order. And I must say there's another assumption that I forgot to mention, which is I also limit myself to those type of operators that won't give me higher than second order equations in the resulting case. So it's useful. It's very useful to guide you in your sort of ignorance about what dark energy could be. But then if you want to study cosmological perturbations, unitary gauge, especially if you want to use Einstein-Boltzmann software, unitary gauge is not a good gauge. So you have to go out of that gauge because you want to go into either synchronous or Newtonian gauge to study your perturbation. So the typical way to make reappear the perturbations to your scalar field, so far I'd call them delta phi, but in here, and typically in this framework you call it pi, is to do this, what is known as the Stueckelberg trick. It's just basically you undo your specific choice of foliation that you did basically with a time diffeomorphism. So you do an infinitesimal diffeomorphism, time diffeomorphism of this type, where you now make reappear the perturbation to your scalar field in this function pi. Okay? And you remember that I told you the way to go to the Newtonian, to the unitary gauge was that you were taking your scalar field and writing as the background one at the time t plus a function of, all right? I swapped between t and tau. I'm swapping between t and tau because we are not doing any concrete calculations, but you have to be very careful. The action I've shown, it's in conformal time. So that will give differences of factors of a and square and whatever in the operators that appear in the action. And so you have to be very careful with respect to which coordinate you do your time diffeomorphism. So basically, by undoing it, you make repop out your scalar degree of freedom, and in particular, its perturbation to it, pi. Now, what happens if you do this time diffeomorphism? Of course, all objects that were entering your metric and are scalar with respect to, they are invariant with respect to 4-dimensional diffeomorphism will be unaffected by this transformation. But objects such as time-dependent function or objects with loose indices will transform and will pick up new terms, and you can do your expansion up to quadratic order, for instance, in the scalar field in pi. Okay? I know, sorry. It's terrible. But okay. So now, if you do the Stueckelberg trick, your action that look very compact becomes huge, becomes long. It takes me more than one slide to write probably the whole action. So I'm going to show you only what comes out from the first line of the action if you do this trick, and if you stop at quadratic order in the perturbations, because still we want to study only linear perturbations. So expand this for all the other operators, and you have your action. You have gone out of unitary gauge, and then now you can specialize to another gauge, such as Newtonian, for instance, to study perturbations. And if you, more generally, you will study also tensor modes, right? Okay, so this one should have come before, probably. And this is what I was saying. So if you try the mapping, you can convince yourself that omega, the conformal, not surprisingly, the function that gives you the non-minimal coupling for f of r will be simply this. And there will be a potential term, no intrinsic kineticity. And if you do minimally coupled quintessence, of course, you expect omega to be 0. C is the kinetic term, and the combination of C and lambda gives you the potential. So you can use this framework in two ways. One is specializing to the models, and you have a specific mapping. But the other one is just saying, I don't know, it could be whatever. I have a number of free functions of time, and I'm going to just vary them and explore my parameter space. Now, why do I have only these? And in the original action, I had 8. I'm dropping some of them. And let's see if I have a slide that justifies that. Yeah, maybe. So let me go. I'll come back to that one. So because there's two ways in which you can approach the background in these theories. You could think of having so look at the first line. The first line, I should say, is the only one that determines your background. All the other operators will become important only for the dynamics of perturbation. So in the first line, you had something like 1 plus omega r, and then there was something like lambda, and then there was something like c of tau delta g 0, 0. Now, you could say, OK, I tell you what omega, lambda, and c are as functions of time, and then you solve for the background. So in order to solve for the background, of course, you have to derive Einstein equation out of that action, specialize to background, Friedmann equations. So whatever choice you make for c, lambda, and omega, you will have a given background. But there is another way in which you can do, which is sort of goes back to the designer approach of f of r, which is I fix h, and I reconstruct my theory. It's a bit more complicated than f of r because you have a free coupling, and so you cannot, specifying h is not enough. You have to specify also for instance, omega, or any other. It's convenient to specify omega because then you get an algebraic equation for C and lambda. So you can specify H and omega, and you're done. Your background is there. Alternatively, you specify omega, lambda, and C, and you have your background. It actually turns out that you don't need 3 of them. You only need 2 of them to fully specify the background. You can convince yourself by playing with these equations that you can drop one of these 3, and it's typically convenient to drop C or lambda. I think it's most common to drop C. So at the end of the day, you need 2 functions of time to completely fix your background. And let me go back to the other slides and the point I made also yesterday. The nice aspect of this approach is that as you turn on the different functions, you're making it more and more complicated. So if they're all 0, you are in the Einstein-Hilbert action. If you turn on lambda and make it constant, you have lambda CDM. If then you make it a function of time, you go into minimally coupled quintessence. If you turn on omega, you go into minimally coupled quintessence. And you keep going. If you turn on other operators, gradually other operators, you go to more complicated models, up to the whole Hordesky. Now, why there are these crosses here? Because, let me see if I had it. I don't remember the way I brought the original action. Yeah, so I didn't take. So this is a bit more than Hordesky. Here, I'm actually, there is an extra constraint that I'm neglecting that makes sure that the equations of motion, resulting equations of motion, are second order. I mean, there are some operators that you explicitly know right away that if you include them, your equations of motion will be higher order. But it turns out that also there are some conditions that you need to impose on some of these in order to ensure that your resulting equations are second order. Ah, I had it here. Oh my goodness. Here. So this function here, and this function here, these 3 operators, you need to combine them in the specific way. It's similar to what happens with the quintic part of the Lagrangian of the Galilean. You have to combine them in a very specific way in order to ensure that your equations of motion, resulting equations of motion, are second order. So you see, you can eliminate 2 of these functions if you stick to Hordesky. And similarly, I told you there's redundancy here in the background, so you can eliminate another one. So you go from 8 to 5. Okay, so now let's see what comes next. Yeah. So I want to make a little bit of contact with another, basically, EFT of dark energy, which is also known as the alpha parameterization. It was originally introduced by Bellini and Savitsky. They have a very nice paper, very insightful paper, where they still work. Well, no, this is not the original starting point. This is when they then reformulated. They were working at the level of equations. They were working in the covariant formalism for scalar field theories, scalar tensor theories. And they played around with the equations for perturbations and tried to group typical terms that will appear according to their sort of observational implications, okay? So they identify some terms that would always introduce a running of the coupling of the Planck mass. And they identify combination of terms that would always imply that your speed of tensor is different than 1, terms that imply that your scalar field has an intrinsic kineticity, and so on. And now it turns out that once you do that exercise, you can also specialize to this AGM language. So again, here you see the lapse function, the extrinsic curvature, etc. And Hordesky becomes so compact. It's very nice. It becomes very compact. Again, you have 1, 2, 3, 4 free functions of time. Let me comment a little bit and then give you the comparison with the other. What are these functions? I told you whenever alpha m is defined as, I think there's a logarithm, I'm not sure, but it's something like d log m star square, I think, in d log a, or something like that. But it's telling you if the coupling, the Planck mass or your effective Newton constant depends on time. It runs. That in FOVAR, it happens, right? For all non-minimally coupled models, you have that. Alpha t is exactly the object that will tell you whether your speed of sum for tensors will be different than 1. So that for FOVAR will be 0. Alpha k quantify the intrinsic independent dynamics of the scalar field. Again, for FOVAR it will be 0. It's called kineticity. Braiding signals any type of coupling between your scalar field and the metric. So for FOVAR, it's non-zero. Yes, what did I say? What? Sorry?
The first one.
Yeah.
Alpha m.
Yeah.
Is the running of Newton's constant.
Yes, m Planck square. It's 8 pi g or m Planck square, right? It's the same. Yeah. Sorry, they use this star, but that's the. Yeah. I mean, up to some things that we put to 1, but typically we exchange 8 pi g for m Planck square, right? Yeah, so, and here, sorry, there's a star instead of a p of Planck. And so, okay, so you see 4 functions, and I just told you that the EFT had 5. So where does the counting, how does the counting go? Yeah, there are 4 functions, but these functions are specific to perturbations. On top of that, you have to separately give me the background. So the way the other formulation of EFT works is that you specify both background and perturbations. This function give you all. These are, so these other alpha m, alpha k, alpha b, and alpha t, and alpha m, alpha b, give you only perturbations. It's assumed implicitly that you know h. So the counting works. You have either h, alpha m, alpha b, alpha k, and alpha t, or you have the 2 approaches in the other case, which I can think as h, omega. I put myself in a sort of similar designer approach, and then I had the mi's. I never remember the 3 mi's. Or you have omega, lambda, and the 3 mi's. Okay? 5 functions, which goes back to the 5 functions that I show you were appearing in P2 plus P3 in mu and gamma, right? And then there was the one for gamma, which had the similar, the denominator equal to the numerator of mu, right? So we keep refining these 5 functions of time. Now, that's, for me, it's the main difference between these 2 approaches, between the language of the original action that I show to you and this one, when you study your, when you sample your theory space. Because if I work in this designer, they're pretty similar, but if I put myself in this case, in which I specify omega and lambda, then it's more like I'm specifying a theory, and I'm finding the h that it gives. And that I cannot do in the alpha language. So that's the only difference, I would say. If you work in this so-called designer, it's basically equivalent. The nice thing of this language is that it's very compact, and it gives you an insight into the implications of the different operators. So if gravitational waves tell us the CT square is equal to 1, I can immediately put alpha t to 0, and I'm done. I have one less function. In the other original language, it's a combination of these that will give me alpha t, that will give me CT square equal 1. So there are some differences, but more or less you did the same.
So both are implemented in the MGCAM?
So this one, the original one that I show, is implemented in EFT CAMB. So in CAMB, and it's called EFT CAMB. I think I have a slide for the 2. This one, and this one is implemented in class, and it's called high class. So, well, I think I might have a slide, or I had it in the first lecture. So high class is the alphas, and EFT combure is born in that omega, lambda, etc. It has also the alpha inside. And I'm not they might have also the same. I mean, of course, you can tell to EFT combure a choice of alpha is it will translate them because there's a mapping. There's a mapping between these alphas and these m's. It will translate them in m's, omega, and then it will work. I think similarly they probably have something, I'm not sure, in high class. You tell them the m's and they translate them. Actually, yeah, so we went to an excruciating code comparison, aiming for sub-percent precision on a wide range of scales for cosmic microwave background, power spectra, etc. And we tried the exercise both specifying alphas and both specifying m's. So in one case, we were the ones having to do the mapping. The other case, it was them. It was a very useful exercise. So you can choose whatever, depending on whether you prefer to work in combure or class. You can choose whatever code.
And both have designer approaches?
Yes.
So you can choose a designer?
You can choose a designer, but both have also specific models. So you can say, I want a Fovar. Well, a Fovar I don't think is in both, but some models are in both. And you can choose, like cubic Galileon, things like that, you can say. And I think you're also working on more models. We are also on our side working on more models. So the designer is there. Yeah, there are some difficulties that I'm not mentioning, in particular with initial conditions. And I've mentioned it when I talk about the Fovar. Of course, if you do quasi-static things such as that intrinsic in mu and sigma, and so in MG combure, the good thing is that you don't have to deal with the dynamics of the scalar field, which can be a pain in the neck at early times, high curvatures. For instance, a Fovar, because the mass of the scalar goes to very high values, and it enters as a sort of 1 over m squared Fovar, multiplying the higher order terms in your derivatives in your equation for the scalar field, it basically gives high frequency oscillations that go, they are harmless for your observables, but they are a pain for the stability of your code. So you basically have to find ways of making sure your code doesn't go through these oscillations. And also initial conditions is something that is very tricky to set in these models. So the simple way out is you say at early times I have GR and then I gradually turn on these functions. One way to deal with these oscillations that are very difficult to control is to what we call, for instance, return to GR. So your code checks how close your EFT functions are to their GR value. And if they are close to, like, I don't know, 10 to the minus 8, within 10 to the minus 8, you say, OK, it's GR. And I won't wake up my extra degree of freedom until this function goes sufficiently away from GR. And that, for instance, protects you from those oscillations. So the inputs are typically, so you have to give a background. So depending on which, so the input can be a background, H, for instance, or W, whatever your code likes to take as an input. Let's say H of A. And the alphas, I think H of A you have to give it, right? Well, yes, so let's say the input is always H of A's and alphas, or H of A, omega, and MI. Unless...
So omega and MI are also functions of A.
Yes, yes.
Everything is functional.
Yes. Or you could put yourself in the case in which you give omega, lambda, and then MI. I think we typically, we don't do it that. We do it in the pure EFT, we do it. But now let's say you specialize to a model. So here you can just choose, I don't know, you choose whatever. You can do expansion of these. And if I tell you I want to do cubic Galilean, you have to solve for the background of cubic Galilean. So if I tell you the cubic Galilean is implemented in the code, it means that there is a background solver that has been attached to the code that solves the background for the cubic Galilean. It outputs then how h of a, how all the EFT function goes, right? Once you solve for the background and you know the mapping, you know whatever, you know how all these functions go, or the alpha, and also the mi, and then you pass them to the code. Okay, and you don't need to pass all. You can choose whether to pass h and omega or omega and lambda. It's desirable to pass h. And yeah, and you have to pass also your background solver has to find the background, the EFT function, and you need also some derivatives of the EFT function that enters in the Einstein equations that you want to be calculated with good accuracy. So that's, I don't think I need to go through this. This is just a snapshot of how your Einstein equations start looking. And this is, which gauge did I put myself? Let me see. Here I think it's the one that we use in EFT-CAM. Yes, it's basically the synchronous gauge with the CAM variables. I'm just showing terms that enters in the Einstein equation as a result of having C, lambda, and omega. I don't have space to show the full equations where all the m's would contribute. This is just to show you if you want to run EFT-CAM. Now this is old. I think we have a new structure. But what you are presented are different flags. So you can choose to go in the standard CAM, so run GR, for instance. You can choose to go in what we call pure EFT, where somehow, besides deciding H, you also give functional forms for the EFT, omega of A, lambda of A, and we propose some choices for the background and for like linear expansion, power laws, and whatever for these functions. But then you go also to well-designer, as I said before, but also specific models, okay? This is very old. And but that's just to give you an idea of the structure. I think we inverted some flags, we have more models, etc.
What is the DBP that is there?
What the?
DBP.
Oh, I don't remember. It's one choice of W as a function of A. I don't remember which expansion it is. I can look it up, but I don't remember. Yeah. This is the code comparison that I mentioned. It was part of our effort in Euclid, in the theory working group, because in particular in the work package that deals with testing gravity, we wanted to make sure all these codes are reliable. So we went to this comparison that involved high-class EFT-CAM and many other model-specific codes. And this is just to give you an examples of comparisons and differences between the spectra given by the two different codes. I don't remember this picture for which codes it was and for which model. I think it was some cubic Galileo for EFT-CAM and I-class, whatever. So we work really hard to keep the difference at basically sub% level. Yeah, this is I have it already. I think I have shown it already. So these are the two larger codes, but then there's many other. There's also a good one called COPE, which is quite broad, but there's many other that are model-specific, right? People that like to study FOVAR or whatever else, they have their own code, either in CAM or class. So we did a lot of comparisons, and we are confident now. So let me think a little bit. This I mentioned already yesterday, the stability conditions. So I didn't show, I showed only this yesterday. How do you approach this stability thing? It's good to go back to the unitary gauge and to look at perturbations of your metric, expanded in scalar perturbations that enters the perturbation of the lapse function, perturbation of the shift as the gradient of a scalar, and then you have your tensor modes and also a scalar field here. And now you take your horrible action and you expand it to second order in these perturbations. And you do a lot of grouping of terms. You see I have Hij tensor, tracelet transfer tensor. I have 1, 2, 3 scalars. You are used that because of gauge freedom, typically you only need to consider 2 out of 4 possible scalar perturbations to your metric. But here I'm in unitary gauge. I've given up part of my freedom, and so I have a third scalar perturbation entering. The good thing is that I'm doing scalar tensor theory with second-order equation of motion, so not all these degrees of freedom will be truly propagating. There are some constraints. So it's a long exercise to expand your action and work out, remove the spurious degrees of freedom. But in the end, you can identify the transverse traceless tensor and the scalar field here as the propagating one. And you can find their quadratic action. And there will be some terms multiplying the kinetic, the gradient, and similarly here. Now, there are some conditions I mentioned yesterday as an analogy. You can think of the harmonic oscillator. And whether you choose wisely the coefficients of the kinetic term, for instance, or the gradient term in the action for your oscillator, you will ensure that you will have oscillatory solution, or you will run into exponentially growing and decaying solution. Similarly, you can do this exercise here. And there are certain conditions that you can impose in order to ensure that your perturbations will be healthy, will not grow exponentially. So the standard one is asking not to develop ghost. That is something with a negative kinetic sign, with a negative coefficient in front of the kinetic term. And then the speed of sound, typically you want it always to be positive, the square of the speed of sound. And that you get it out of a combination of the gradient matrix, here it's a gradient coefficient only, and the kinetic term. And similarly, you can do that in the tensor sector. This is just a basic set of conditions of stability that you can impose. There's more things that you can work out. And you have always to be, there's a lot to say. You have to be careful. Here we are looking at stability without matter. I'm completely neglecting the action for matter. It turns out that the action for matter, if you properly treat your matter components, you then have a matrix basically for your scalar degrees of freedom. You will look at a kinetic matrix, a gradient matrix. And in doing the proper diagonalization, etc., the result is that the speed of sound of this, what you like to associate as the speed of sound of the scalar degree of freedom, will have some contribution from matter fields. So it's all entangled. It's a very complicated exercise. And then, of course, there are certain stabilities for which you can say, I really want to avoid them. Some others for which you have to think about the time scale over which they develop. Because maybe they develop so slowly that they will not show up during your expansion history. And so in principle, you can say, I don't care. I can have it. So it's still ongoing work. There's a lot that we need to work out and make sure that it's correct. And why I say that? It's very important because it has a strong impact on the parameter space. So the first thing we checked out was, OK, so let's say I go to W0, WA, of course. That's the simple exercise that you can do by hand. But what are the regions of the parameter space that I exclude depending on the different stability conditions? And in here, now I don't remember the dash, I don't remember exactly what it was. But so you can rule out regions of your parameter space if you ask your EFT to study a model that is a simple, minimally coupled quintessence characterized by W0 and WA. So it means you're opening only lambda and C, and omega you set it to 0, and also all the other functions. And so, for instance, EFT at that point will understand that you don't want to cross the phantom divide because you're killing all the other operators, so you won't have anything that will prevent you from developing a ghost. You can open other operators, and then you will be able to access the W0, WA part that is non-phantom. Similarly, we check for the parameter space that is typical of a FOVAR on a WCDM background, so a background for which you have W constant but not equal to 1 possibly. And this is the typical 1 free parameter that you are left with a FOVAR. So you can study a FOVAR within the EFT language. And stabilities will tell you that you have a very restricted parameter space in where to study. So these are data contours. And we have derive them after cutting, from a theoretical point of view, the parameter space. So the idea is you don't waste time in exploring regions that don't make much sense, which is great, but it has two drawbacks. One is that sometimes the stable parameter space is very pointy, and then it becomes really difficult to properly sample those regions. And the other drawback is that this whole stability, as also the question that I got yesterday made it clear, is a very tricky business. So you have to be careful, because whatever you impose a condition can have a strong impact on the parameter space that you tell people to explore. So I think it's very good, it's a very promising avenue, but there's a lot of work to do. And let me finish with this EFT by telling you a bit more about what I showed yesterday and the way we want to use it. So I was saying we want to build these theoretical priors, which goes back to your question about how can we build guidance for the data exploration with data. And the way we are trying to do it is by classes of models. So for instance, we take Hordesky, and then we put ourselves in the case in which we don't specify the background, but we specify the functions. And we try to expand them in many different ways as function of the scale factor. Trying to be very general, we expand around today, around the past, so that we allow for freezing and towing models. We try to go to different upper bounds here in the sum. I think here I'm writing 9, but we check that if you stop at 5, not much changes. And we explore also wider range for these coefficients, etc. Of course, these are choices. Yes? I'm parametrizing. So as much as I'm trying to be very general, there will for sure be some impact of my choice, right? As I was saying yesterday, for instance, for when this quasi-static regime breaks, I'm sort of implicitly inputting a mass scale. So there's always a limit. But so we do this, and then we sort of Monte Carlo sample all these parameters, creating 10 to the 8 different models. And you could think of them as 10 to the 8 Hordesky models. And then to this model, we impose stability conditions. So they go typically down to something like 10 to the 6 models. And then we look at the phenomenology. What's the cosmology that comes out from those models? And we create these contours. So this is 1, 2, and whatever sigma contours, but on the theory side. We have done a Monte Carlo on the theory space. And I'm telling you what Hordesky generally gives for W. Here we have, well, let me start from here. What I expect for W in Hordesky up to some sigma, right? I have a theoretical distribution. Now, up here, we have specialized to the subclass of quintessence. As I was mentioning yesterday, one other problem in this approach is that because of the way you sample, any theory, so let's say I expand omega, lambda, and c, any theory that corresponds to c being equal to 0 is basically a measure 0 in my sampling. So that's why we go gradually. And so we look at quintessence separately. And here you see the bound coming from stability conditions, right? It doesn't let you go, because I'm doing minimally coupled single field quintessence. So it doesn't let me go below -1. If I do full Hordesky, I can start going. It doesn't like to go that much below -1, at least for these expansions of us. But so you can sort of start seeing features and broadness of the distribution, and you can start seeing where it likes to depart from -1, etc. So you can build some intuition about what to explore with data. And you are free always to take this distribution and project them in your beloved parameterization, such as W0, WA, and get an idea of where your contours would be. Now, that was for W, but of course, I told you you can do it also for mu and sigma. That's what I was showing yesterday. And you can do it in 2 ways. One way doesn't require any Einstein-Boltzmann solver. It requires only to expand your functions. Here I've hidden all the EFT function into this F1, F2, M, etc. you can expand your EFT functions as functions of time. And then you can simply use the quasi-static expression for mu and sigma. You don't need to evolve perturbation and nothing. And you have them. And of course, you use your stability sampler to check that you are looking at stable models. Or otherwise, you can run your EFT camp or high class, get the full perturbations, and out of there, read the full mu and sigma. So those are the two things that I had, red dots and black dots, yesterday. So we went through this exercise. Let me skip this. I might go back to it. This. So we went through this exercise of, again, sampling Hordesky and projecting it into mu and sigma. I might have, let me see if I have. Yeah, so we can create, then I'll go back to the others. We can create, similarly to the distribution that we did for W, we can do it for sigma and mu. Look, I'm neglecting k dependence in here, okay? So I'm showing you a sort of slice at a given k, because mu and sigma in principle are function of time and scale. What we have seen, and I'll highlight when I show the clouds, is that it depends mildly on k. But of course, that again depends on where you have your mass scale. And so, okay, these are just things that we can learn about expected distribution for mu, sigma, and W in Hordesky here, generalized Brans-Dicke. And what is this HS? It's the subclass of Hordesky that have CT square equal 1. Okay, and so we can build theoretical priors. So the main thing that we want to get out of this is this thing, this correlation and covariance matrices. This is just a plot, but you have the matrices. And in particular, we can read correlation length. So we can understand the typical correlation length, so the typical length scale over which this function change and show some dynamics for given class of models. And that thing is very useful to build a correlation prior, something that if you want to do a binning, a PCA approach to your functions, gives you a guidance on how many bins to choose and how much the bins will be correlated. So that's how we are trying to use them. But let me go back to the clouds. So here I'm looking at different scales. There's no much dependence. Here it is. In going from this 10 to the minus 3 to this 0.05, here is where somehow my length scale probably that I have somehow chosen through my parameterization is sitting. That's where quasi-static breaks. But then the other feature, as I was highlighting yesterday, is that the models tend to align a lot along this direction. This is almost general Hordesky with one constraint, which is CT square equal 1 today. So it's the most, it's the loosest way of implementing the bound from gravitational waves, saying basically LIGO has measured CT square being equal to 1 at redshift 0.01 or something like that. So it's today. I might still have a way of making it non-1 earlier. So this is, if I do that, if I instead ask CT square to be equal to 1 at all times, it really narrows down along the diagonal. It opens up a little bit at late times. What this diagonal is telling me is that at earlier times, and almost on all scales, at least all scales relevant for Euclid, I will not expect to see, if the true theory is Hordesky, I will not expect to see any shear, any anisotropic stress that function eta or gamma, that was the ratio of eta or gamma, that was phi over psi. I don't expect to see it. It doesn't mean necessarily that the growth of rate will be the same as in lambda CDM. Still mu and sigma can be different than 1, but they have to be equal. So that's very stringent. It's a very narrow region. OK, so I think that's all I wanted to say about EFT. And since there were some question about screening, and I kept mentioning that it's good to go beyond the spherically static symmetric configuration, I wanted to just sketch something, show you something about that. So as I said, one thing that you can do is try to go beyond spherical symmetry. Now, we started to do that. I never finished this project. So I might be showing something that is not entirely correct in the next slide when I give equations. Claire Burrage has a nice paper where she studied ellipsoidal configurations. But this was back at the time in which I was at MIT and talking with Ed Bershinger. We were thinking that it would be really nice to look at what happens with the screening in the presence of a two-body system. And then we said, OK, that's very complicated. Let us start in a perturbative way, sort of thinking of the second smaller body as a sort of perturbation away from the spherical symmetry of the main body. And so that's when I started to play with these spheroidal sources and never finished. Don't write it down, but you are very welcome to check it. So I try to reproduce the calculation that I showed to you for the spherical case. Again, homogeneous. It's an approximation, right? It's very unlikely that it's almost impossible to have a spheroidal configuration, oblate spheroidal. I'm looking like here. It's a surface of revolution from an ellipse around its minor axis. So something that is an oblate spheroidal and has a homogeneous and static density distribution. That basically doesn't exist in nature, but you can do it mathematically, right? So the thing is that now you're giving up spherical symmetry, but you still have some axis of symmetry, and you can reduce still the problem to a differential equation in one coordinate if you properly go to the spheroidal coordinates, okay? And so you have a very similar equation, just with slightly different form to the one that you were used to have in the spherical case. It becomes less obvious to understand how to separate in the three regions, the regions in which you expect your scalar field to go to the minimum inside, which shape. That's the main question. Which shape do you give to these shells that separate the different regions? Do you expect them to follow the symmetry of your source, or do you expect these surfaces, this shell, to be spheroidal as well or not? And that, I think, needs to be checked numerically. So here in the equations, I'm showing stuff that I did analytically. And in order to proceed analytically, I did assume that the different regions were following the symmetry of the source. I, of course, tried to set up this numerically with the relaxation method, first as a one-dimensional problem. So again, thinking that my scalar field will follow the symmetry of the source. But I also set up a relaxation code in 2 dimensions, so allowing the scalar field to depart from the symmetry of the source. And so you can check. I think if I remember correctly, it was very close to the symmetry. Now, what I found, both analytically and numerically, but I'm not sure it's correct. So it's just to stimulate you if you want to work on something on screening to do it, is that there was a sort of critical oblateness, critical ellipticity of my source. And when it was becoming too squeezed, the screening was breaking, wouldn't work. There was no way to create a thin shell configuration. I found it both analytically and numerically, but it doesn't mean that it's correct. But it's an interesting thing. You do see, there might not be this critical oblateness, maybe, but you do see, and that's also what Claire Burrage and I don't remember the other, it was a student of her in the paper found. You do see that it's a sort of, you get a sort of lightning rod effect. Indeed, there was a very nice paper by Francesc Ferrer and somebody else back in the years talking about analogies between chameleon and electromagnetism and the lightning rod effect. So you do see that screening becomes very little efficient. Here I'm looking at the gradient in my chameleon. So you remember, if it goes through a thin shell, it means that if it goes to a thin shell, it means that around the source, so you have your source, and we were saying that it is at the minimum, and then over a very thin shell, it goes towards the value at the cosmological background. And this is, it has a steep gradient here, right? but it's very limited in region. If you go through a thick shell, it basically changes throughout your source. So the gradient is milder. So that's what you're seeing here. You are sort of inefficient at screening around the flatness direction, and where the curvature of your source is higher, you have the screening that is still very strong. Of course, it changes depending on your oblateness. As you decrease the oblateness, you go closer back to the spherical symmetry. That's also a good check of your solution, that you reproduce what you know for the spherical symmetry. So it's interesting. I wanted just to mention this because it gives us a hint that screening mechanism in general, and Einstein also particularly, respond a lot to the symmetry of the source. So there are some some lab experiments of fifth force screening mechanism, and they do play with looking at the forces and the fifth force between two sources, and a lot of work goes into choosing the ideal shape of these sources in order to maximize or minimize. Actually, you want to minimize the effectiveness of the screening, so you hope to pick up your fifth force if there is one. The other thing that you can do, as I mentioned, is to abandon staticity, but you want to do it conserving spherical symmetry. And so the first thing that you can do is to think of something that is radially pulsating. So that's another exercise that I did back in the years, trying to go from the background configuration of so thinking that I have a spherically symmetric, static, homogeneous, isolated source which achieves thin shell. And then I perturb it slightly by introducing these pulsations that are radial. And I look at these are the perturbations that I put on top of the source, and I try to look at the solution delta phi that will sit on top of this thin shell. What happens so I treat it perturbatively. Now I will have an equation that has not only the spatial coordinates, but keeps also time coordinate in here. I have the full D'Alembertian. I still preserve in spherical symmetry, so I have only the one spatial coordinates. And because of the fact that my background solution was the thin shell, I have a sort of effective scale-dependent mass now for this perturbation in the chameleon. And there is a source. So I try to solve this, again, analytically. You can do quite some progress if you go in Fourier space. There are some things that you can learn as an insight from these equations, but let me show pictures. So you do see that the chameleon picks up this pulsation as perturbation that basically propagates as a disturbance into the surrounding space, so will affect your metric around these sources. And that's there's also many other papers than especially after gravitational waves, the detection of gravitational waves came out, because this is telling you that you can have monopole component and also dipole component into your radiation that you expect out of some sources. So it's interesting. It would change, for instance, it would change the rate of energy loss through gravitational radiation and so on. The main interest that I had, I never followed up on this, but the main interest that I had when looking at this situation that was initially a thin shell, but then I was perturbing it, was thinking of collapse. Because I was very interested in seeing whether there is a strong time-dependent situation where, for instance, your source collapses, let's say supernova or something like that. The energy that is captured in the thin shell, you eventually go to from a dense, but some source that has a radius. If it collapses to something that cannot sustain anymore the thin shell, you would expect all the energy that was captured in this thin shell configuration to be radiated away. So that's why I was interested in studying this. Back of the envelope calculations convince us that it would be negligible, and also keep going with this homogeneous distribution. I mean, there's pressure, for instance, that comes into the game. And you remember a chameleon couples to the trace of the energy momentum tensor. So all I showed so far was only the static spherically symmetric stuff with non-relativistic matter, so only the trace of the energy momentum tensor was given by rho. But pressure in those violent situations will play a role. So it's not an easy and it's not an easy problem, but maybe it's something to look into. Okay, I'll almost stop, so there's some time for a question because then I have to leave sharp at 10:30. You had question about principal components, so I went back this morning to some old slides. That's why it's very different style. And I don't have time to explain them, but I just want to show we did this exercise of taking a grid in scale and redshift, using ranges that would be sort of relevant, especially for the redshift, for upcoming surveys such as LSST, and creating this pixel, and on this pixel we would treat mu and sigma or mu and gamma as a known function, and we end up with something like 800 parameters because then we have many pixels for each of the two functions. I give a value in the pixel. These are my new parameters. Then I have the cosmological vanilla parameters, some bias parameters, etc. So I end up with a huge number of parameters for which I calculate the Fisher matrix, and we were concentrating on things such as galaxy count, weak lensing, etc. And then I do a diagonalization, and I read out the eigenmodes of this matrix. And I can do it, for instance, separately. I can think of looking at mu while I marginalize over gamma and all the other cosmological parameters. I can also look at combined eigenmodes where I don't want to marginalize. It's a very, it would take the whole hour to go through this, but I just wanted to flash some plots. So here it's looking at the eigenmodes that you get for the function mu. The two important things, what are the alpha m, these coefficients in the expansion of your function in the eigenmodes, and the eigenvalues of your diagonalized matrix, which tell you the precision, the sensitivity that your experiment will have to these coefficients alpha m. Okay, so what you learn is typical shapes that you expect to pick up with your experiment, and with which precision, and how many of these you expect to pick up with your given experiment. So this is just showing you the first eigenmodes that we expected to pick up with LSST for mu and gamma. The main thing that I want to say out of this, of course, you see there is an increasing number of nodes, but we were seeing that they are mostly in K. Okay, the first eigenmodes, we couldn't detect any time dependence in this function. And why? Because of the high degeneracy with all the cosmological parameters and the background parameters. What else do I want to show? It might be more informative. So speaking about this sigma, which comes from the eigenvalues of your diagonalized matrix, doesn't have an absolute meaning. Then you need also to compare to signal to noise and whatever your experiment. It gives an idea, so it's always better to compare the sigma for different things, either different functions or different experiments. So if I specialize to an experiment, here LSST, I can compare this sigma for a different principal components of my functions, mu, gamma, marginalizing, non-marginalizing, so I can learn which one will be best constrained. So gamma will be the poorest constraint, of course, from LSST. Mu will do better, a combination of them. And then if you put into the game sigma, of course, LSST will do much better on sigma than gamma. Okay, this was just only to show you something, but it's a lot. Okay, and then I wanted to say a few things to close. This is, since we were talking yesterday about Dutch and Netherlands and Brazil and whatever, there's a very nice option, not for you, but for your fellow bachelor students all over the world that I want to mention. We have this bachelor summer school in Leiden. It lasts 2 weeks. They really treat you well. There's a lot of funding, and you sit through lectures from all of the faculty members of the physics department, so you get an idea of all the research that is done there and things that you could study for your master. They take you to nice visits to the ESA site in the Netherlands. You are given a bike if you like to bike, so you can, and housing, etc. It's really nice, and you get exposed to a lot of research, both theoretical lectures but also lab visits. And now they have also a new thing I've just heard, where there's, I don't know if it was only for this year, but I think it will be also for more years to come, where the Brazilian bachelor students that were at this school could submit a proposal for a master project or bachelor, maybe for the bachelor or bachelor project, maybe some 6 months bachelor project, to be done with the PI of the Lyon, of the Leiden Institute of Physics. And there's some funding for that. So some of them will be selected and will have the chance to come back for 6 months and do some research. So I think it's a very nice opportunity. This is a link. So if I'm sharing the slides, so if you click on it, it takes you. There's also a video that is a sort of commercial for the school. OK. And then I wanted to conclude with some thanking the organizers. I've never been to Brazil. I love it. It's a wonderful country. I've seen only Sao Paulo and very little of Sao Paulo because you kept me very busy. But I loved it. It was really nice. And thank you. The organization of the school was great. I'm amazed by your dedication, by sitting through all the lectures, sitting here all day, asking very smart questions, going through the whole hour of question and answer. I'm really amazed. Thank you. And I really made good friends. It was lovely to share this week with the other lecturers and Vivian. That was great. This is why I didn't manage to prepare the calculations for today, because yesterday they derailed me. I was really working on it, but OK. And we are quite, I don't want to say rich, but the research in the Netherlands has quite some money. I cannot complain about funding, and I'm always very happy to spend funding on having visiting students. So if you're ever interested in visiting Leiden, in coming to collaborate and whatever, just send me an email, and we'll try to accommodate for that. And I stop here. Thank you.
Thank you, Alessandra. So you still have 5 minutes.
5 minutes, yes. I tried to stop earlier.
Questions for Alessandra? Yeah.
Maybe coming back to the PCA thing,
Okay.
actually what you do is you do the principal component analysis and you compute the cumulative variance, and then you see that you don't need to consider 800 parameters, but only 100 or so. It's just because it's amazing. You showed to us that there is a specific, I think, for the LSST.
Yes,
I think it's the last plot.
Yeah. Here.
No, previous one. Yeah. You have the big dimensional reduction here, right, for the gamma marginal
big
line.
dimensional reduction.
So it seems amazing what you can do with this for forecast.
Yeah. No, indeed, we have several papers on this. But the one thing, though, is that when you actually go to the true fit to data, you don't really want to say, OK, I have 10 good, let's say 10, roughly, rule of thumb, modes that will be measured. All the others, I throw them away, because it's a sort of implicit assumption that they will be sort of measured exactly to be 0. So you're sort of contradicting yourself. So that's also where we want the theoretical priors to come in. But yes, I agree. And it's a very good guidance. I didn't show the results. We use it at some point with true data. I was mentioning yesterday the question and answer. But that was CFHT lens. So we had like 2 beams in space and 2 beams in time, so something like 4 components. But yeah, it's a good exercise. We are doing it right now. I should say we are doing it. I have very preliminary and probably wrong results, so I'm not going to share them. But we are doing it for mu, sigma, and W simultaneously with all like Bose, Planck, all the possible data, and using the theoretical priors out of Ordesky. And so, yeah. hopefully something interesting will come out.
And PCA is amazing, really, to reduce the dimensionality.
But it's, I mean, I wasn't the one doing the actual numerics that is behind that, but it's a pain in the neck.
Yeah. Any further questions for Alessandra? So if not, well, first I want to thank you for coming down to Brazil to give this nice set of lectures. Down, yeah.
No, right.
And,
winter, I was enjoying summer.
Yes, winter.
That summer is worse than the winter here, so.
And I'm sure you'll be back. So,
Yes.
so thank you very much for this great set of lectures. Thank you.
Thank you.